In the synthesis of palmitic acid, we first needed EACP-SH complex, which we then react with Malonyl-CoA and Acetyl CoA and use the enzyme malonyl-acetyl transferase. So this is an acetyl CoA with 2 carbon atoms, and then we have our Malonyl-CoA with 3 carbon atoms. Now this Malonyl-CoA and Acetyl CoA gets added to the complex in this way. First, the sulfur here, it gets bonded to the Malonyl-CoA. I'm showing the Malonyl-CoA using the red one. And the sulfur over the enzyme, it gets bonded to the Acetyl CoA. So the negative charge over the oxygen will donate its electron with the carbon, and the adjacent carbon single bond will break, and that bond's electrons will get donated to the COCH3 of the acetyl CoA, and then the single bond bonding the CO and S will go and bond with the hydrogen here. This will basically give us SCOCH2 and the acetyl CoA there COCH3, and over the enzyme E we will have SH. So we are basically just combining the Malonyl-CoA and the acetyl CoA together, except for the end CO group of the Malonyl-CoA leaves as CO2. So in this complex we have 4 carbon atoms bonded to the sulfur. And the enzyme we use here is beta-ketoacyl ACP synthase, as we are forming a beta-ketoacyl ACP. Now using a beta-ketoacyl reductase, we will reduce this beta-ketoacyl ACP, and for reduction we use NADPH+, which gets converted to NADP+, and then here in the beta carbon we will reduce the keto group to an alcohol group, and the rest of it stays the same. And now as we have reduced the keto group, the new name would be beta hydroxyacyl ACP. In the next step we use the enzyme beta hydroxyacyl GCP dehydratase, the short form DH, and we remove the OH from here, and we basically dehydrate this complex. That means we remove water from here. The rest of the complex will be same, except for in the beta carbon the OH will be removed, thus we will get the carbon double bonded to the adjacent carbon here. Now as we have a double bond here, so the name of the structure will be enoyl ACP. In the next step we use enoyl ACP reductase again, and then we reduce the double bond here to become a saturated carbon-carbon single bond. Now again, while reducing, we will convert NADPH H+ to NADP+. Now we get an acyl ACP. In the next step, we use methyl acyl transferase, and the carbon complex bonded with the sulfur over the ACP will get transferred to the sulfur over the enzyme. Again, we use MAT in the next step, and we use Malonyl-CoA if we want to get a longer fatty acid chain. Complex over the enzyme will stay the same, and we'll get a malonyl group bonded to the sulfur over the ACP, just like in the first step. Now the same steps will occur as in the second step. The carbon dioxide will leave, and then CH2 will bond to the C, double bond O, and sulfur will get an hydrogen. Now here we got a higher number of carbon atoms. We'll then repeat all the steps 2, 3, and 4. After repeating all the steps, we are gonna get 2 more carbon atoms getting bonded to the original carbon chain. So here we'll get 6 number of carbon atoms. And as palmitic acid has 16 number of carbons in its chain, we need 10 more atoms bonded to these 6 carbon atoms. And as we add Malonyl-CoA. With each Malonyl-CoA, we get 2 carbon atoms bonded to the fatty acid chain. Hence, we'll need 5 more Malonyl-CoA to add 10 more carbon atoms to the fatty acid chain. So we'll repeat the steps 1, 2, 3 and 4 5 times with Malonyl-CoA. Here are the steps 1, 2, 3 and 4. After step 4, we have 4 carbon atoms in the carbon chain, and doing the reaction twice gives us 6 number of carbon atoms in the carbon chain. And if we repeat it 5 more times, we'll get 5 2s are 10 more carbon atoms in the chain. Now using thioesterase, we can break the C double bond O and S bond. So we'll get an enzyme ACP-SH complex, and we'll get our palmitic acid fatty acid chain.